Okay, so welcome, and let me start by saying Happy New Year and welcome to the first lecture this year. I suppose maybe you've had other lectures, I'm not too sure. So, Happy New Year once again, and uh, I wish you very prosperous and fulfilling year. Uh, Today we are going to discuss the chapter 7 of the course textbook, which focuses on sample size determination and hypothesis testing. Uh, Already you have seen the uh, lecture outline and the specific objectives for the lecture. Sample size determination and hypothesis testing are two critical concepts in statistical inference. To determine the correct sample size ensures reliable and precise results. Hypothesis testing, on the other hand, provides a systematic way to make decisions about population parameters based on the sample data. So we are going to explore these two broad concepts: sample size determination and hypothesis testing. So by the end of the lecture, you will be able to understand the importance of determining an appropriate sample size. Two, you will learn how to calculate sample size for both population means and proportions. Three, you should be able to grasp the fundamental concepts of hypothesis testing, including null and alternative hypotheses. Four, you should be able to differentiate between errors in hypothesis testing. So we'll talk about two types of error in hypothesis testing: the type 1 and type 2 errors, and how we interpret p-values. We will be able to apply hypothesis testing to real-world problems and at the same time draw meaningful conclusions. So, but before we go into the lecture proper, as usual, let's just look at few pre-lecture uh, multiple choice questions to prepare us. Uh, the first one is, why is determining an appropriate sample size important in statistics? A, to minimize bias. B, to ensure the results are representative and precise. C, to eliminate all errors in data collection. D, to reduce the need for hypothesis testing. Are you able to make a choice? Are you able to make a choice? Why is determining an appropriate sample size important in statistics? Can you just choose any size as your sample and go on with it? What will you achieve? So I can't see any response yet. Are you responding? Okay. Wonola, at least I can see Wonola making uh, a choice. Lati player. So the correct answer is actually B. We the reason is to ensure the results are representative and precise. Choosing the appropriate sample size will help you to ensure accuracy and also manage your resources. Uh, we all say resources are limited, so uh, you don't need to take more than necessary samples. Another question is, what is the primary factor influencing the width of the confidence interval? We discussed this in our last lecture. So that should be easy. Sample size, population size, sample mean, test statistic. What are the options for question 2? I'm yet to see anyone responding. Okay, so Lati is going for A, Wonola is going for B. That's good. So let's move on because of time. Others are joining. That's good. So the correct answer is A. Sample size influences the width of a confidence interval. If you take large samples, that will shrink the width, and then shrinking or reducing the width implies that you are uh, increasing your precision. So the accuracy is uh, improved or better. Next is, which of the following is not part of hypothesis testing? You've not done this, but this is to prepare you for the lecture. Um, so A, formulating the null hypothesis. B, calculating the test statistic. C, conducting a census of the population. And D, determining the p-value. Which of the following is not part of hypothesis testing? What are your choices? What are your choices for 3? Fedayo C, Wonola C, Festus C. I think consensus is around C. The correct answer is C. Conducting a census is not part of hypothesis testing. Hypothesis testing relies on sample data, not on the entire uh, universe, not on the population. So, uh, conducting a census is not, part of hypothesis testing. Now, question 4 says, what does the null hypothesis represent? Again, this is also uh, a concept that we will discuss shortly. But uh, if you have heard anything about it, you should be able to come up with a choice. The claim, A, the claim that is always false. B, the effect or difference in a study. C, the assumption of no effect or no difference. D, a hypothesis that is rejected only when p-value is greater than 0.05. Which of these does the null hypothesis represent? What are your choices? Uh, the responses are coming very slowly. Fedayo A, Raymond C, Player 1 C, Mutamina C, Festus A. Okay, let's see what the correct answer is. C. The assumption of no effect or no difference is what the null hypothesis represents. And this forms the baseline of statistical testing. So the starting point, the baseline, is to say there is no difference or to say there is no effect. We will discuss that again very shortly. Finally, for this pre-lecture quiz, the question is, what is a type 1 error in hypothesis testing? A, accepting the null when it is true, rejecting the null when it is true, failing to reject the null when it is false, failing to reject the null when it is true. What are your choices? I hope you can make a good guess. Abayomi says B. I think that's the only response for that. That says C. Urala says B. Uh, yeah, Montamina says B. Ibrahim. Okay, let's see. Those are good attempts. The correct answer actually is B. So when we say type 1 error, it is the error committed by rejecting the null when it is true. So And this error is very critical. So we need to uh, learn how to manage and control it. So we'll discuss that also in the lecture. The second type of error is called type 2 error. So the two errors will also be discussed in the lecture. So let's go to the lecture proper. Uh, so let's start with the introduction to sample size determination. And the question we want to ask ourselves is, why is this so important? Uh, as mentioned earlier, sample size plays a vital role in ensuring that our results are representative and reliable. It's always important uh, to be mindful of how we select, uh, how we determine our sample size, and also how we select the samples from the population. So the reason being that, one, if our sample size is too small, that can lead to inaccurate conclusions. And if our sample is too large, that will lead to waste of resources. So we want to just choose sample size that is just adequate enough to guarantee accurate conclusions, and at the same time to optimize the resources available for the study. So we don't want to take uh, too much or samples, that are too much, and at the same time too few. So factors affecting sample size include the desired confidence level that we choose, the margin of error. We have discussed all these concepts. For instance, the desired confidence level could be 90% confidence level, could be 95% confidence level, could be 99% confidence level, or any value in that range, 90 to 99. Uh, so your choice of confidence level will affect the sample size. The margin of error will also affect the sample size. We discussed the concept of margin of error in our last lecture when we are constructing confidence interval. So the margin of error for confidence interval, the range is determined by the formula estimate, if you recall, uh, estimate uh, plus or minus margin of error. So we use estimate plus or minus the margin of error. So the margin of error determines the width of the confidence interval. So that also affects the sample size. The third factor that affects the sample size is the population variability, which is measured in terms of the population variance. We have also discussed that before. So don't forget those uh, three factors, but we'll see how they affect. So looking at that formula, that expression that you see, you will notice that uh, that formula says sample size is equals to the product of Z and standard population standard deviation divided by the margin of error, all square. So that is the formula for computing the appropriate or for determining the appropriate sample size. That formula is derived from the margin of error. As you, if you go back to the last lecture. So to determine the appropriate sample size, you need to determine three things, three quantities. One is the confidence level, and you need that to be able to determine the Z score. So the Z score that corresponds to the confidence level you have chosen will be used. In the last lecture, I gave you the Z score for 90% confidence level to be 1.645. For 95% confidence level, the Z score is 1.96. And for 99% confidence level, the Z score is 2.576. You can also read those values directly from the standard normal table, the statistical table. So once you have those three quantities, you can just substitute and calculate the appropriate sample size for your study. So let's look at the example there. That example is saying, suppose you want to, this example is saying that suppose you want to estimate the average weight of maybe human, could also be animal, could also be any object. You want to estimate the average weight, and you know the margin of error as well as the standard, the population standard deviation of the weight of the population. So you can then substitute the values in this expression. So for this particular case, uh, the margin of error is 2. The Z, that's the standard score, is 1.96, which means our confidence level is 95%. So, and then the population standard deviation is 10. So sometimes it could be the confidence level that will be given, and you will need to determine the Z. You could also be given the Z score, and that could help. You can also obtain the corresponding confidence level. So substituting those values there, you get approximately 97, which means that if you want to ensure precision in terms of the average weight that you want to estimate, then you need to take sample size of 97. That the appropriate sample size to take is 97 to ensure precision of the estimate. So always remember that you will need those 3 parameters, or rather those 3 values: quantity, the Z score, the population standard deviation, and the margin of error. For the Z score, it is you or the researcher that will decide. So you can choose, as earlier mentioned, you can choose 90, 95, you can choose 99, or values within that range, no problem. So once you know the confidence level, 96%, 92%, 98%, you can choose. You will only need to now go to the table to determine what the appropriate Z score is, and you use that as your Z. And then, who determines the population standard deviation? Yes, sometimes you don't know because you don't have information about the population. So later we will discuss how we handle that. But the procedure is to use the sample standard deviation. So for now, we are assuming that we know the population standard deviation. But if you don't know, you have to estimate it from the sample. The third one, margin of error. How do you determine that? So again, it is the researcher that will determine that, what level of error you can tolerate or you want to accept. So you determine that. So you will see invariably that the researcher has a role to play in determining the sample size, and a number of factors will have to be considered, as earlier mentioned. So let's now look at how to compute the sample size for a population proportion. The previous one is when we are that formula is used when our interest is in determining the sample size for a population mean. But if our interest is that of population proportion, then the formula is different, as we have noted earlier. So for population sample size for a population proportion, the formula is given as this, that the sample size is the square of the z-score multiplied by the proportion of success and proportion of failure, which is 1 minus p over the square of the margin of error. So in this formula, you know everything. Maybe, the p is easy to determine. That's the proportion of success, and just 1 minus p. So you have three quantities to determine there: the z-score, the proportion of success, and of course the margin of error. And then you apply the formula accordingly. So in this example, our interest is to conduct a survey to estimate voter support for a policy. So you maybe population of the citizens in the country, or population of uh, uh, students or whatever, and you want to estimate what proportion of the population support the policy. So what is the appropriate sample size that will make the estimate of our proportion to be accurate or reliable? So to determine that sample size, we need to provide information about the confidence level. In this case, again, we have chosen confidence level to be 95%. And that's why the z-score corresponding to 95% confidence level is 1.96. The proportion of the population that and support of the policy is 0.5. So we assume 50%, of the population we support. And then the margin of error is 5%. So we could choose another value, but we don't want our estimate to exceed 5% in terms of the margin of error. So we have all the values now, and we can substitute in this expression. So we have the sample size, approximately to be 385, which means you need 385 sample drawn from the population and then observe their uh, support for the policy. So that will help you to get uh, an estimate of the uh, voter support, the proportion of the uh, voter that support the policy, uh, and that proportion will be reliable because you have taken the appropriate sample size. Any sample size below this will give you inaccurate uh, estimate of the proportion. It could be more if you take 500, for instance. Fine, that's good, but you will be spending more resources than necessary. That's the implication. So therefore, if you just take 385 or within that, you could make provision for those who will be unwilling to participate. You can adjust, just add few to that and so on like that. Uh, but you have a good idea of this, uh, this appropriate sample size. So that's how far as we'll go as far as sample size determination is concerned. So uh, we now know the formula for determining sample size, for mean and also for proportion. And we also now know those factors that can influence the sample size that you choose. So the Z, the confidence level that you choose, uh, the margin of error that you are willing to accept, and of course the population variability, in the case of mean, and then the population, uh, uh, the proportion of success in the population in the case of uh, proportion, in the case of sample size for a population proportion. So if there are questions, feel free to put it in the chat menu. Yes, I can see Dada Ibrahim saying, I noticed in the approximations that 384.16 was approximated to, yes, 385. Why not 384? Yeah, that's a good question. Since we are talking of sample size, one, there is no half human being, no 0.16 human being, or even animal, or even any object. So since you are selecting individuals, so you can approximate downward, upward. Uh, that's why you have 384. Yes, Nagiat, I'm also responding to how 384 tons, 384.16 tons to 385. I hope that is clear now. So if I'm selecting two people from your class, uh, will I also be able to select 1.5, 1.5 people from your? So if I calculate my sample size to be 8.4, so what I can do is to either round it to 9 or round it to 8. So I can round up or round down, so that I will be able to I will get rid of the fraction there. Excellent. So Dada, I think you got it. I don't know if Nadia also agree with that explanation. So if you agree, just type yes. If not, okay. So nobody else is responding. So if I say my final answer is 383, is that correct? Well, it's still correct, but um, why are you going to 383? You want optimal sample size. So it's even better uh, to choose 384 and just stay there, or you choose, but going down to 383 uh, may make it slightly suboptimal. That's the implication. So if we, do you want to start going down again? Nagiat Osishu. So if I say 383 is okay, then you want to go to even 300. So, yeah, Nagiat, maybe to be on the safer side, you can round up rather than round. Uh, we actually round up. We rounded up in this case to uh, 385. So that's a good one. Uh, let's move on to the next uh, next issue uh, on our agenda. So that is hypothesis testing. Most of you must have heard about hypothesis testing. So hypothesis testing is just a structured procedure for making decisions based on sample data. We all make decisions uh, every day. Um, Decision like should I join this YouTube, this virtual lecture, or should I not join? Decisions like uh, uh, should I uh, come to school uh, by Okada or by Marwa. We choose by a particular means of transportation. So you take decisions from time to time. But hypothesis testing um, is a structured approach, a systematic approach. It's a statistical approach for making decisions about the population parameters based on sample data. So the steps involved are listed. There are 5 major steps, and we are going to take each of them one at a time. Uh, the first step is that you need to formulate the hypothesis. And how do we formulate hypothesis? We formulate hypothesis by simply specifying the, the null, which we call the H naught, and the alternative, which we call the H1. Sometimes also you have, instead of 1, you have it as H subscript A. So the first is called the null, and the second is called the alternative. So there are only 2 uh, hypotheses, the null and the alternative. So That's the starting point. You have to specify what is your null and what is your alternative. Then the second step is to choose a significance level. To choose a significance level. In the last lecture, we discussed about the confidence level and side by side with the level of significance. So you recall I told you if your confidence level is 90%, then your significance level is 0.1, 10%. Or we say 0.1. If your level of confidence is 95%, then your significance level is 0.05. If your level of confidence is 99%, then your significance level is 0.01. So the significance level is the complement of the level of confidence. So remember that. So in the second step, you have to choose. So if you choose confidence level to be 95%, for instance, then you know that that translates to 5% significance level. So from your confidence level, you can obtain your significance level. So you have to choose which level you want: 90, 95, 99. After that, the third step is to calculate the test statistic. The test statistic again could be Z, which is uh, normal. We could also have other test statistics like T, chi-square, F, but not we won't discuss all of that in this course. So in subsequent course on statistical inference, you will get to know some of them. But the one we will discuss here is the Z statistic, the uh, the normal statistic. And the fourth step is to now determine the p-value or critical value. We will discuss the two in detail. Why do we need to determine these two values? You can choose, you can choose one of them. It's either you determine the p-value and take your decision, or you determine the critical value and use it to take your decision. The two are basically tools for arriving at a decision. And the decision is the last thing you have to take. And that is step 5. And that is where you now take a decision about the null hypothesis. About the null hypothesis. So you can reject the null hypothesis, or you fail to reject the null hypothesis. Somebody may ask, why do I not just say reject or accept? Well, I won't go into the technicality of that, but we avoid saying accept because it gives the impression that once you accept, is uh, like a court declaring um, a suspect as innocent, you know, uh, or as a saint. Uh, True, one may not have committed an offense. Uh, it doesn't make the person um, to be innocent or to be a saint. Uh, it's just that the available evidence at the moment doesn't really support the claim made by the prosecutor. So um, it's either we reject or we fail to reject the null hypothesis. Those are two options in terms of decision. But the hypothesis that we are focusing on under the decision is the null hypothesis. Though it has implication on the alternative. So if you reject the null hypothesis, so it implies that yes, the alternative, uh, uh, the evidence available is actually supporting the alternative. And if you fail to reject the null hypothesis, it simply means that the evidence in your data uh, is not strong enough to reject the null hypothesis. So let's go into each of these steps and see it uh, how it works. So let's start with uh, is there any question? Let me check if there are questions. Uh, so I cannot see any questions so far. So as said earlier, the first step uh, when you are conducting hypothesis testing is to specify or to formulate the hypothesis. And that involves you stating the null as well as the alternative. So we usually put versus. So the null versus the alternative. So the null hypothesis, what does it connote? What does it mean? That is the hypothesis that assumes no effect or no difference. So it simply represents the status quo. That is, it that's the hypothesis that states what we know at the moment, or what you know is the what the current knowledge is about the phenomenon that you are trying to investigate. So it represents the status quo or no effect. For instance, you can say in the case of uh, population mean, you can say the average height or average weight of the population is 50 uh, kg, uh, or the average uh, score uh, in the test, is, or in the exam, or in the uh, assessment is 50. So that is the null hypothesis, which means is saying what the population mean is what is known about the population mean. That is it. The alternative, on the other hand, is always contradicting the null. So, and that is why if the null says it is 50, alternative will say it is not equals to 50. Uh, there are other things. It could be directional, which means the alternative can say is greater than 50. That is directional. The alternative could also say is less than 50. Again, that is directional. So when it is not directional like this, that's when we say it's two-sided. It's neither less, so it could be either less uh, or greater than 50. So the concern is that it is not 50, but it is something else other than 50. So, but the point at this stage is that when you are formulating your hypothesis, you have to specify the null, which is the one that states no effect, or states no difference, or simply gives what the status quo is. The alternative is the one that specifies the claim or the effect that you are testing, or the difference that you are testing. So, uh, so once you do that, that means you have been able to formulate the hypothesis. So it must be clearly defined before you even go for data collection. This hypothesis formulation must be done even before you begin to talk about data collection or doing any calculation about uh, the validity of the test. Some people uh, often abuse this procedure. What they do is to collect the data, run the analysis, see the results before they now formulate the hypothesis. That is very, very wrong. So less is the, uh, the type 1 and type 2 errors. So you must know that when you are taking decision about this hypothesis, it is possible to commit two errors. So, uh, for instance, you can have, I mean, Generally, if you have the state of nature, this is the state. This is the state of nature. So which may be true or false. And your conclusion could be true also or false. And you don't know the true state of nature. This is state of nature, which could be true or false. And if you conclude that it is true when it is actually true, then you are correct. So no error has been committed. This is correct. But if your conclusion says true when it is false, then you have committed an error. That error is what we call type 1 error. The error you commit when you uh, when you reject the correct hypothesis. So then, if your conclusion is false when the true state of nature is when nature is true, but you conclude that it is false, then again you have committed an error. That type of error is called type 2 error, which is false negative. If you conclude that it is false when it is truly false, you have not committed any error. That is correct. So we have two errors. So this is type 1 error. This is type 2 error. So type 1 error is false positive. Type 2 error is false negative. So by definition, type 1 error is the error of rejecting null hypothesis when it is true. So type 2 error is the error of failing to reject the null hypothesis when it is false. So these are the two possible errors one can commit in hypothesis testing. But the most serious one, actually, maybe I should leave that to you to determine which of these two errors is most serious. Um, but at this point, it is important to know that we always want to reduce errors as much as possible. But since we are likely to commit two errors, the problem is that as you want to reduce one error, then you end up inflating the other error. So therefore, you have to see how you will ensure judicious balance between these two errors. And that can be achieved only by taking appropriate sample size and also, you know, choosing the right significance level. So you have to balance the appropriate sample size and the significance level. So for now, it's just appropriate for you to know what type 1 error means and what type 2 error means. Type 1 error is committed when the null hypothesis is rejected when it is true. While type 2 error is committed when you fail to reject the null hypothesis when it is false. That's what that's the definition for now. The alpha is actually the probability of committing type 1 error, and beta is the probability of committing type 2 error. So you must understand these two errors in statistical or in hypothesis testing. If there's any question, let me know. Good. Now let's move to another important concept. We have said that we need to formulate hypotheses. We need to formulate, we need to formulate in the steps. We need to formulate the null, the alternative. We need to choose a level of significance. We need to calculate the test statistics. Then we need to determine the p-value or the critical value. So here now, we want to talk about the p-value. The p-value measures the probability of observing sample data, the sample data, or something more extreme, assuming the null hypothesis is true. We've talked about the normal distribution. So if you have data, this is usually the point where the observations are mostly concentrated. That is at this point. So if you are interested in a particular value, so the p-value measures the probability of observing this value, let's say Z, that observed value, that gives you the probability of observing any value that is any sample value or extreme value, that is value that is above that sample data. So the p-value helps to now decide whether we should reject the knot, whether we should accept the knot, the H knot, whether we should reject the null or whether we should fail to reject the null. We will accept the null if that p-value, if the value we are observing falls into this side, this unshaded side. But if the value falls into this part, then we will fail to reject. In other words, if the value is here from this point, if it's anywhere here, and particularly talking about this side. So if the value should fall here, then you will fail to reject the null. But if the value is here, anywhere in this unshaded area, then you'll be able to you fail to reject. Sorry, when it is here, you fail to reject, and when it is here, you reject the null. So the role of p-value is to be able to decide whether to reject your null hypothesis or to not know, or you should no, you should not, whether you should fail to reject your null. So I'm avoiding using the word accept. So p-value determines whether the null is rejected or whether we should refuse or fail to reject the null hypothesis. So, and I repeat, if the p-value is such that is in this part that is shaded, it means the p-value is very, very small. It's very, very small. So in that case, you reject the null hypothesis. But if the p-value is larger, which is in this shaded area, then it implies that we should not reject the null hypothesis. Do not reject the null hypothesis. So that is the role of p-value. Is basically meant to take a decision about the hypothesis that you have formulated. And the rule is what you see there. If the p-value is less or equal to the level of significance, if it's smaller, less or equal, if it's less or equal to the level of significance, then you reject the null. If the p-value is greater than the level of significance, then you fail to reject the null. So it simply means you can have a line here, and this is if this is you have this is your so this is your alpha. So if the p-value is smaller than or equals to the alpha, then you reject your h naught. So if it is less, if p is less or equal, then you reject. If p is greater, then you fail to reject. So you fail to reject. Take note of that. We have example. Let's say here that you have you are testing an hypothesis where it's about proportion, and the hypothesis is saying uh, h naught, that the proportion, oh sorry, okay, the hypothesis, let's look at the example here. The example is, let's start with the example of testing for a hypothesis, testing for a population mean. We will come to the proportion later. So in this particular example, we are testing for population mean, and we are saying that h naught, the population mean, is equals to 50 versus the alternative, that the population mean is not equals to 50. That is the hypothesis we are testing. That is the hypothesis that we are testing. So we have formulated the hypothesis by that, that expression, saying the null, saying that the status quo is that the population mean is 50 versus the alternative, that the population mean is not equals to 50. Remember, the alternative always counter the null. So the next thing is to, if you go back, after specifying, we need to choose our level of significance. So in this case, if we choose our level of significance to be 5%, which means our confidence level. So we choose alpha to be equals to 0. Point, point, 0. I don't know why this is 0.05. 0.05 or 5%. You choose the alpha. Then the next thing is to calculate the test statistic. That is the third step here. We have done this. We have done this. The next thing is to calculate the test statistic. So we will now need to use this expression. And we are using this expression because we assume that the population standard deviation is known. Remember, it may not be known, but we will discuss how to handle that later. So for now, if the population standard deviation is known and the sample is large enough, remember we discussed about small and large sample. So if the sample size is large enough, then we can use the z-test. The formula for the z-test, which is the z statistic, the formula for the z test is given as what you have there. The sample mean minus mu naught. Mu naught is the hypothesized value. In this case, it is 50. That's the value that is hypothesized. That is the value that is claimed. So, and then the standard deviation, since is known, you have been given. In this case, the sample mean is 52. So, and then sample size is 100. So we can substitute that to be able to get the value of the z. So that z-test statistic, this is what we call z-test statistic. The value is 2. And after we have computed this, that is when we will now need, let me take you back to the next step, which is either we determine the p-value, that is step 4, is either we determine the p-value and use that to arrive at a decision, or we determine the critical value and use that to arrive at a decision. So here now we will see how to go about getting the critical value or calculating the p-value to enable us take a decision. So how do we read the critical value, the z-score critical values, and how do we calculate the p-values? We are going to start with the z-score critical value. If you have been following in the previous lecture, we've talked about z-score, which is calculated using that expression. So Uh, why is it important? No, uh, the Z-score helps us to determine how unusual or how typical a data point is within a distribution. Uh, of course, the distribution in particular is the normal distribution. And uh, we have seen before that the critical values associated with the confidence levels are what you see here. So if your confidence level is 90%, which implies that your uh, level of significance is uh, 0.1, 0.1, then the corresponding critical value is 1.645. It is like uh, so for 95%, the for 95% confidence level, the corresponding level of significance would be 0.05, and the critical value will be 1.960. Why we are putting plus or minus there is when we are dealing with two-tail tests. For instance, if you have your plot, so this is the center, this is the center where you have the mean, and then the the so you could have uh, one standard deviation away from the mean. You could have two standard deviation away from the mean. So, but you could also have on this side, you know, minus one standard deviation away from the mean, two minus two standard deviation away from. So uh, the 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 Z score, the Z value determines the width, the standard deviation away from the from the from the center. So if you are talking of a two-tail, then let's say this is so you could have uh, plus or minus. So if it's plus, it's talking about this. If it's minus, it's talking about this. So you could have uh, the same value, you know, 1.645 uh, from the uh, from the center. So this, so you can read the Z value, the Z score on the horizontal axis. So you can use table to read, use Z table or statistical software to find the area under the curve. So we could find the area under the curve uh, using the uh, the Z table. This is a typical Z table, for instance. Let me share the screen. Let me share. Okay. So this is a typical Z table. I So this is a typical standard normal table which you can use to read the value of Z. So if for a standardized distribution, the mean will be equals to 0, and then the values here have been standardized. So here you have 1, you have 2, you have 3. So this is one standard deviation away from the mean, 0, 2 standard deviation. Be careful, because you could have different versions of this table, but I've chosen this. So what this one says is that it's always measuring the shaded area, from the positive side. So if you have Z value and the proportion of the shaded area for the Z's, for the proportion of the shaded area gives you probability value, and that's why every value here is less than 1. So for instance, uh, if I'm interested in the value, the proportion of this shaded area, that the proportion of the shaded area from 0 to 1, then I will come to Z equals to 1. This is it. So I have that to be 0.3413. Let's say I want between -1 and 1. Then it means, since the curve is symmetrical, then I can add that 0.3413 and just multiply it by 2. So that will give me 0. Point um, uh, 6826, something like that. So while you can use it to read probability, you can also use it to read what the corresponding Z value will be. So that is what is of interest to us at this moment. So in our case, remember we have our Z value to be our level of significance to be 0. Our level of our Z, um, our uh, our Z. Let's go back to, let me change the screen again so that we can see. Yes. Um, we have to move between windows right now to be able to follow closely. So critical values 1.645, 1.960, 2.576. These are critical values, and they can be read from the from the table. So, for instance, the table that I showed you before, we can easily read these critical values from that table. So now that we have our so the question now is, what is the critical Z score for a 95% confidence level? That's what we want to determine now. The critical Z value for a 95% confidence level. So as I said earlier, for a 95% confidence level, the corresponding level of significance, which is alpha, is 0.05. Yeah, we could go this way. Since our hypothesis is a two-tailed test, it's a two-tailed test because the alternative is saying not equal to. So if it's a two-tailed test, then we have to divide the alpha by 2, and that gives us 0.025. So it's like you have your plot this way. So since it's a two-tailed test, it could be on either side. So this part is 0.025. This part is 0.0. This is the center. So we now need to find the Z value where the cumulative area under the curve is 0, where the cumulative area under the curve will give us 0.1 minus 0.025. I will explain how that is, but I will need to change this screen again. So if we now, just a minute, go to the so we are going to use our table again. We are going to use our table again. So from the screen is coming up. Just a minute. I hope you are able to see the screen. Yeah, so the screen is up now. I hope it is very clear. Okay. I hope it is very clear. So we need 0.9797. No, we need to read the cumulative probability for Z equals to 2. So for Z equals to 2, we have to come to this. This is Z equals to 2. And for Z equals to 2, which is saying when Z is equals to 2 here, so you have the value to be 0.4772. So which means the total area from 0 to z equals to 2 here is 0.4772. But that what we need actually is it includes this part, so that it's going to be everything down cumulatively, and this part is 0.5. What we read here is only given from a 0 to 2. So therefore, 0.5 will be added to the value that we have here, which is 0. So we add 0.5 to this 0.4772, and that's how we obtain the cumulative probability for z equals to 2 to be equals to 0.9772. So let's go back to our slide. I will need to change the screen again. Usually it takes time. Just yes. So here we have. So that is the so that gives you the the value of 0.9, yeah, for the cumulative probability of z to be 0.9772. So that means our p-value will be equals to, so our p-value will be equals to 2 multiplied by 2 multiplied by 1 minus 0.997772, because of the two-tailed test that we are testing, and that will give us 0.456. So that is the p value, but the critical value is 1.960. So we could either take a decision based on the critical value or based on the p-value. So if we go by the p-value, we've said that we will compare the p-value with the alpha value. So if the p-value is smaller than the alpha value, in our case, the alpha value, the p-value that we got is 0.0456, 0, 4, 0, 4, 5, 6, and our alpha is 0.05. So if the p-value is less, then as it is, the p-value is smaller than the alpha value. So which means we have to reject the null hypothesis. We have to reject the null hypothesis. And what that implies is that we have evidence against the null hypothesis. But if the reverse is the case, then it means the evidence is not sufficient for us to reject the null hypothesis. So I've explained this, how we calculated the p-value, everything that I was trying to do there here. So this is the z value that we computed. This is the area that I mentioned, which is 0.9772, which is the cumulative probability when the z-score is equals to 2. This is the, because it's two-tailed, this is the value for the p-value, which is 0.0456. And since the p-value is smaller than the alpha value, then we reject the null hypothesis. Rejecting the null hypothesis simply says that the population mean is not equals to 50. The population mean is not equals to 50. So this is the process for taking a decision, for conducting statistical test of hypothesis. So in summary, z-scores are used to determine how far our data point lies from the mean, from the center. And the critical values is used, or rather define the boundaries for rejecting or failing to reject. So the p-value rather quantify the strength of the evidence that we have against the null hypothesis. So we can always compare the p-value with the significance level to be able to draw conclusions. And we have also seen that sample size affects the precision and reliability of our results. So, and that is why it's always important to determine the appropriate sample size. We have also seen that hypothesis testing helps us make informed decisions about our population parameters. They are not based on conjecture, they are based on a systematic procedure. Then we have seen the two types of error that can be committed. The type 1 error, that's the error of rejecting a true hypothesis. And the type 2 error the error of accepting a wrong or false hypothesis. So p-value is crucial for accurate interpretation. So we have been able to also apply to various practical examples, and we have seen how we can take a decision. So it's very important we understand this concept for data analysis and interpretation of results in statistical research. So this is where we are going to stop today. But as usual, I have questions, but because our time is now, we will just run through the questions. If you can catch up, that will help me to know if you are following. I cannot see any questions so far. I cannot see any questions. So let's quickly go through the questions. What does the sample size formula what does the sample size formula for a population mean depend on? The sample size formula for a population mean, what does it depend on? We show that it depends on three things. It depends on three things. If you recall, margin of error is there, the confidence level is there, then the population standard deviation. So the correct answer is B. The sample size formula for population mean depends on the margin of error, the confidence level, and the population standard deviation. Question 2. What is the purpose of determining sample size before conducting a study? Why do you have to decide the sample size before you conduct a study? Is it to reduce the population size? Obviously, no. Is it to ensure results are accurate and representative? Yes. Is it to eliminate all sampling errors? No. Is it to guarantee the null hypothesis is rejected? No. So the correct answer is to ensure that the results are both precise and representative of the population. Question 3 says, in hypothesis testing, what is the significance level? In hypothesis testing, what is the significance level? The probability of making a type 1 error, the probability of making a type 2 error, the confidence level of the test, the difference between the null and the alternative hypothesis. Of course, this is straightforward. The answer is A. The significance level represents the probability of rejecting the null hypothesis when it is actually true, and that is the type 1 error. So your alpha or your level of significance is actually type 1 error. Don't forget. What is a type 2 error in hypothesis testing? So a type 2 error, A, rejecting the null when it is true, B, failing to reject null when it is false, C, rejecting null when it is false, D, accepting null when it is true. Obviously, B is the correct answer. So when you fail to reject null when it is false. So B is the correct answer. So type 2 error occurs when we fail to reject the null even though it is false. We are supposed to reject it when it is false, but if we fail to reject it, then we have committed a type 2 error. And you have a question here that, you know, if, for instance, your uh, P, that is the uh, your P is 0.03, that is the P value is 0.03, and your alpha is 0.05. What should the conclusion of the hypothesis be? We know the decision rule. The decision rule says you should reject if the p value is less than the alpha value. So in this case, the p value is 0.03, which is less than alpha value of 0.05. And therefore, the correct answer in this case is A. So since the p value is less than alpha, we reject the null hypothesis, which implies that we do not have sufficient evidence against the null. Question 6. What happens to the standard error when the sample size increases? The standard error, what happens to standard error when the sample size increases? A, it increases. B, it decreases. C, it remains unchanged. Uh, uh, D, it depends on the population size. We've said this before. The correct answer is B. The standard error decreases, when you take more and more sample. That improves your precision estimate. Which of the following is an example of a null hypothesis? A null hypothesis is usually stated in this in, in take the difference, of no effect, no difference. So the mean test score is not 75. The mean test score is greater than 75. The mean test score is equals to 75. The sample mean is equals to uh, uh, 75. So in this case, C is the correct answer. The mean test score is equals to 75. The null hypothesis represents the assumption of no difference, no effect, or typically stated as equality. 8. What is the formula for the test statistics of a population mean when the population standard deviation is known? The correct answer here is B. Straightforward. So the correct answer is B. Question 9. What does a p-value represent in hypothesis testing? We've said it before. The probability of rejecting H naught when it is true, it is not. The probability of obtaining the observed data if H naught is true. That is the correct answer. B is the correct answer. The p-value is the probability of observing the sample data, or something more extreme, assuming the null hypothesis is true. Finally, for a one-tailed hypothesis test, if the critical Z value is 1.645 and the test statistics is 1.8, what is the decision? So you are not using p-value in this case. So you are using the critical value to compare with the test statistics. So if the test statistic if the test statistics exceed the critical value, then you reject so the null hypothesis. The test statistics is 1.8, which is greater than the critical value, so we reject the null hypothesis. Thank you very much. This is where we end the lecture for today. I hope you were able to follow. Uh, if you follow, please let me know. Just type yes in the chat menu. If you follow, you are welcome. So see you next week. Bye for now.